Hello, everyone. Happy Tuesday. I hope you all had an amazing long weekend. So we are going to talk about today trophic levels and the laws of thermodynamics, which are kind of cool, and maybe you will achieve enlightenment after learning about this. All right. So the first law of thermodynamics says that energy can change from one form to another, but it cannot be created or destroyed. So a good example of this is if you're pushing a ball up a hill, that's a type of kinetic energy. Eventually it's going to get to the top of the hill, and all of that kinetic energy used to get it up there is now potential energy. And if you were to give it a good shove, it would turn back into kinetic energy as it rolled down the hill. Another example of this is when we eat food. We don't just magically make our own energy. Obviously, if we don't eat food, we die. So that's how we get our energy. We don't just magically create it. We take the energy stored in this burger, we break it down, and maybe we use it to dance, which would be kinetic energy again. All right, so this is not one of the laws of thermodynamics, but this is the law of conservation of mass, or the conservation of matter. So matter cannot be created or destroyed. So basically, big picture, is that when we eat our food, the atoms in our food are not destroyed by our stomachs. We break down those chemical bonds, and then we use those atoms in our food to build our own molecules, which means you literally are what you eat. Any of the unwanted material or any unwanted matter, any of those atoms that we don't need, we excrete or poop out. So we can't just magically create matter out of nowhere. We have to use already existing matter in order to create new materials. Gotta love Leslie Knope. Gotta love her. All right, so trophic levels. One sec. Let's try this. So trophic levels. We kind of talked about this already, but we have primary producers. These are going to be plants. Then we have primary consumers. These are going to be herbivores. All right, sorry about that. All right, so we were talking about trophic levels. So we have the plants here, and then we have the herbivores. Secondary could be omnivores or carnivores. And then tertiary are most likely going to be carnivores. These are also going to be carnivores. All right, so we have primary producers, primary consumers, secondary consumers, tertiary, and then all the way up to quaternary. And as we go up these different trophic levels, we're not only passing on energy, but we're also passing on matter. Remember, you are what you eat. So all the matter found in this caterpillar is going to go to this frog, and so is all of the energy. All right, let's see if All right, so energy will change from a more ordered state. So this is the second law. Man, this is kind of hard to do, huh? This is the second law of thermodynamics. Energy will change from a more ordered state to a less ordered state when being converted, which basically means it'll increase its entropy and heat will be lost to the environment while we're converting energy. So entropy just means disorder. So a good example of the second law in action is when you are exercising. All right, so you're turning chemical energy in your body into kinetic energy. So that's the conversion that's happening there. And when we're doing that conversion, we're going to lose a lot of heat to the outside world, which is why you start to sweat and get hot when you work out, is because of the second law of thermodynamics. So when the conversion is happening, it's not a perfect conversion. Not all of the chemical energy gets turned into kinetic energy. There's going to be a lot of heat lost to the environment. And this is because of the second law of thermodynamics, if you take this to its logical conclusion. So once energy is lost as heat, it's not easily usable. So that energy that's radiating off of you every time you run, the universe can't use that heat. So there's a theory, it's called the heat death of the universe, that eventually, after so many different conversions of energy, all of the energy in the universe will be heat because of the second law of thermodynamics, which means it is unusable, and there will be no more energy left that can be used, which is why it's called the heat death, because then living things would not exist. So kind of crazy. It won't happen for a very, very long time, but kind of cool to think about its logical conclusion. Oops. All right, so the second law of thermodynamics has a big effect on our trophic levels. So this is called the 10% rule. So you can see here that at each trophic level, you have heat coming off. So the 10% rule basically means that as we go up the trophic level, only 10% of energy is actually passed on to the next level. So if we start off, let's say the plants have 20,000 kcals per meter squared per year. Remember, that's our primary productivity number there. That's how much energy they store. So remember, this is going to be our NPP here. The amount that's passed on is only 10%. So if you get a problem like this on the AP exam, you could multiply 20,000 times 0.1 on a calculator. But a really easy way to do 10% is to just move the decimal place back 1 point. So instead of 20,000, we are now at 2,000 kcals per meter squared per year. All right, and then another 10%. So remember, this is because of the second law of thermodynamics. During this conversion, there's going to be a lot of energy lost as heat. Also, they're using up a lot of energy here. So from 2,000, we go to 200. And then move our decimal back 1 place, 20. And then all the way up to 2. So there's some implications. So you can see that we're in a triangle. So the triangle exists not only because as we're going up, there's going to be less energy available at each trophic level, but you'll see there's also less organisms at each trophic level. Because there's less energy available at the top, there's going to be less organisms that can live in the quaternary consumer category at the top of this trophic pyramid. Just because there's less energy, there's not as much energy, which means there can't be that many quaternary consumers in an ecosystem. Whereas there can be a lot of producers for only about one quaternary consumer. So that's another implication, is that as you go up the trophic level, there's also going to be a decrease in biomass as well as a decrease in available energy, which logically makes sense why those are coordinated. All right, erase real quick. There we go. All right, so we have this thing called, we had NPP and GPP. Now we have GSP and NSP. So this is gross secondary productivity, which is total energy consumed. So GSP equals food eaten minus fecal loss. So this is the amount of energy that stay in our body. And then we have net secondary productivity, which is the gain in energy or biomass after respiration. So this is why we gain weight right here. So if we eat more food than what we use to go through cellular respiration, we will store that. That will be our net secondary productivity. If we eat less If our GSP decreases, is less than our respiration number, we're going to not store as much in that number. That NSP will actually be negative. But for trophic pyramids, this also is another explanation for why the 10% rule exists. So not all of the food we eat, we store. We use a lot of that in cellular respiration as well. All right, so I want you guys to work on today your interactive notebook. There are only 2 slides I think I added, or 3 maybe, for today's work. And then there is a New York Times article on Flipgrid. If you have any issues with Flipgrid, please let me know. I hope you guys all have an amazing day, and I will see some of you tomorrow and some of you on Thursday. Bye, everyone.